Okay, so next, we are going to, I'm going to, give you the statement of the central theorem, but I'm going to ask you to prove it yourself because it's very easy to prove, okay? So the central theorem of complex analysis is Cauchy's integral theorem. Okay? And you can show this. And I'm going to give you a hint at the end of the statement. So I want you to try this, okay? At home. Let U be a simply connected region. Do you guys know what a simply connected region is, right? Is there someone?
No, sir.
Okay. So suppose U is this thing. It's a subset of the complex plane, right? So that means that it's simply connected if any loop within U can be continuously deformed to a point. Okay? So this is an example. But let's look at a domain that is not simply connected. So for example, let me use a different color. Suppose that U is this annular region, okay? Then obviously, this loop, you can, you can shrink it to a point, but this loop, you cannot. So therefore, the second one is not simply connected. Another way of saying that U is simply connected is to say that the first fundamental, group of U is the identity group. The first homotopic group is just identity, okay? It's a trivial group. So that's one way of saying U is simply connected. Okay, do you understand?
Yes, sir.
Well, it just means that there is no holes in U. Okay. So suppose that U is a simply connected region, and f of z is holomorphic. Is holomorphic in U as well as on the boundary. Okay. So that means that anywhere in U, f of z is finite and its derivative with respect to z bar, and this is often used notation, is 0. Okay. So if that is the case, then any closed contour, then if gamma is any closed contour in U, then, so for closed contour integral, we use this symbol. And sometimes we use this because the contour is always, when we are doing contour integrals, we are implicitly traversing the contour in the counterclock direction. It's just a convention. So f of z, the contour integral of that around that closed contour is 0. Okay, so that means that if I go to my simply connected region and say, if I take a closed contour and I do a contour integral on this closed contour, it's going to be 0. Okay? And the assumption that we are going to make, assumption is that the first derivative of f exists. Okay? This is the assumption you need to prove this. So this is Cauchy's integral theorem. And let me give a hint. Hint is use two-dimensional Stokes theorem. Okay, and this is a technical assumption. So let me make a comment. F prime Z exists is a technical assumption. You can prove it. You can prove the theorem without it. But the proof becomes much more involved. Not hard, involved. Okay, you can look that up too. Okay, can you guys try this at home?
Oh, yes, sir.
So first first look at the result for Stokes theorem, and what Stokes theorem will give you is it'll give you the the line integral with some it'll if you take a vector function, a two-dimensional vector function, and you do the line integral of the vector function on, say, on a contour, Stokes theorem will connect that to the curl of that vector function, in the middle. And the curl, of course, involves derivatives, and that's how you can, connect the integral of a function to its derivative. And at some point, you have to use the fact that the derivative is related to the Cauchy-Riemann condition. Okay, so use 2D Stokes theorem and plus Cauchy-Riemann equations. Okay. Okay. Any questions? I mean, of course, I haven't proved it, but it's a pretty easy. Like, you should be able to understand what this theorem means quite easily, right?